In this video, let us learn about how a 2-input CMOS NAND gate is being constructed and how it works for various combinations of inputs. Let us now construct a CMOS NAND gate. To construct a 2-input CMOS NAND gate, we need 2 PMOS transistors and 2 NMOS transistors. 2 PMOS transistors P1 and P2 should be connected in parallel. 2 NMOS transistors N1 and N2 should be connected in series. 2 PMOS transistors will work as pull-up network. 2 NMOS transistors connected in series will work as pull-down network. Now let us see, we have 2 inputs as said, one will be named as A, other one as B. A is connected to P1, B connected to P2. Similarly, in pull-down network, A is connected to N1, B is connected to N2. We can interchange this connectivity also. This is the circuit schematic of a CMOS NAND gate. The other figure here shows the symbol of CMOS NAND gate. This is a normal NAND gate symbol which can be used for CMOS NAND gate also. The truth table here is a NAND gate truth table where we have 2 inputs and 1 output. Input can be 0, 0, 0, 1, 1, 0 or 1, 1. For all the possibilities, the output are also been given. The expression equivalent to CMOS NAND gate is A into B the whole bar. Whenever we design a CMOS NAND gate, we will have only the complementary outputs. That is why we always design a NAND gate. So now let us see how this NAND gate works for various input combinations. The first input combination is considered to be 0 and 0. So A will be equal to 0, B is also equal to 0. The same value 0, 0 is fed inside the circuit. Now the PMOS transistor P1, P2 both will have inputs 0 and 0. Similarly, the transistors N1 and N2 will have its input 0 and 0. We all know that PMOS transistor switches on when the input is equal to 0. Therefore, for the combination A is equal to 0 and B is equal to 0, the transistor P1 and P2 as well, both will be on. Therefore, it means that there is a path for VDD to move to Vout. That is the load capacitor available at Vout. Now it has an opportunity to charge itself to VDD. Therefore, your output will be equal to 1, equal to VDD. VDD is equivalent to logic 1. And now look into the circuit schematic. It has been highlighted using red color that P1 and P2 is on. On the other half, pull down network, both the transistors N1 and N2 will be switched off. For the input combination, A is equal to 0, B is equal to 0. Therefore, there is no path to discharge also. Therefore, the output is strictly 1. Now let us consider the input A is equal to 0 and B equal to 1. For this input combination A is equal to 0 and B equal to 1, the transistor P1 is on because A is equal to 0. The transistor P2 is off because B is equal to 1, because we very well know that PMOS switches on when the input is equal to 0. And similarly, in the pull down network, when A is equal to 0, N1 is switched off. When B is equal to 1, N2 is switched on. But there is no continuous path for the load capacitor of Vout to discharge itself to VSS. On the other hand, when we look into the pull-up network, there is a path from VDD to Vout through the transistor P1, which has been highlighted. So, VDD will be connected to Vout through the transistor P1. Therefore, the load capacitor can charge to VDD. Therefore, the output logic will be equal to 1. For the third input combination, A is equal to 1, B is equal to 0. For A is equal to 1, the transistor P1 is off. For B is equal to 0, the transistor P2 is on. On the other half, in the pull down network, when A is equal to 1, N1 transistor is on. For B is equal to 0, the N2 transistor is off. When we look into the pull down network, there is no continuous path for Vout to discharge itself to VSS. On the other half, when we consider the pull up network, the transistor A is equal to 1, therefore P1 is off, and the other half, when B is equal to 0, P2 transistor is on. Therefore, there is a path for VDD to Vout through the transistor P2. Therefore, the load capacitor at Vout is now able to charge to VDD. Charge to VDD means the output logic equivalent is equal to 1. Therefore, when P1 is off but P2 is on, there is a path through P2 for Vout to charge itself to VDD. Therefore, your output logic will be equal to 1. Now let us consider the last input combination of A equal to 1 and B equal to 1. When both the inputs A and B are 1, both the PMOS transistors P1 and P2 both are in off state. Therefore, there is no path for Vout to charge itself to VDD. On the other hand, when we consider the pull down network, we have transistors N1 and N2. Both are switched on because of your input A is equal to 1 and B is equal to 1. So now we have a continuous path for the load capacitor at Vout to discharge itself to VSS. Therefore, there will be no stored charge. It is completely discharged. Therefore, the output equivalent logic will be 0. So thus your output will be 0. So now for this input combination A is equal to 1 and B equal to 1, both pull up network transistors P1 and P2 will be off, and pull down networks N1 and N2 will be on, and there is a path for output Vout to discharge to VSS. Therefore, your equivalent output will be 0. We have designed a CMOS NAND gate, and we have seen how this CMOS NAND gate works for various input combinations of 0, 0, 0, 1, 1, 0 and 1, 1 so far. If we want to design an AND gate, it is very easy. You have to use a same CMOS NAND gate logic structure, and at the output of CMOS NAND gate logic structure, we have to add a CMOS inverter. Therefore, the inverted output will be the expected output of an AND gate. I hope the construction of CMOS NAND gate and its working for various input combination is now clear. Thank you.